Hello again. This is section 3.4, real zeros of polynomials. So what we're going to look at in this section is if we're given a polynomial and we want to find all the zeros of that polynomial, how can we do that? How can we figure out what are even the possibilities of those zeros? And then what can we do to actually find which ones actually work? Okay. So our rational zeros theorem here tells us that if we have a polynomial, okay, and that's that same general form of a polynomial we've looked at before, has integer coefficients, a of n, again, a sub n cannot be equal to 0 because that would make the leading coefficient a 0, and we can't have that. And then a sub 0 also not equal to 0, because in this case, we need that constant term to exist to be able to find some possible rational zeros of our polynomial. Now, as long as both of those things are true, then we can actually look at all of the factors of the constant term, all the factors of the leading coefficient, and then we can divide all of those combinations to figure out what are the possibilities for our rational zeros. Okay, so P in this case is a factor of the constant, Q is going to be a factor of the leading coefficient, and then we're just going to divide all those things and figure out which ones could potentially work. Now, once we know which ones are possibilities, then we'll actually test and see which ones are the actual zeros of the polynomial. All right, so we're given a polynomial here, p of x equals x cubed minus 3x plus 2. We want to find all the rational zeros of that polynomial. Okay, so again, the way we're going to do this is we're going to think of the p-values, which are just going to be the factors of the constant term. Okay, so that's where we're going to start in this case. And so here we have 2, which is a plus or minus 1, and a plus or minus 2. Now, the reason we have to use plus or minus is because in this case, I could combine a negative 1 and a negative 2, and that would give us a positive 2. I could also have a positive 1 and a positive 2. That still would give us a positive 2, right? So we have to use the plus or minus because we will have some combination of positives and negatives that will give us that last term now. Now, the Q values are going to be the factors of our leading coefficient. In this case, that's an understood 1. So the only factors of 1 here are plus or minus 1. And again, we need the plus or minus because positive 1 times positive 1 would give us 1, but negative 1 times negative 1 would also give us a positive 1. Okay, so you're always going to want a plus or minus in every single instance. Okay, you're always just going to put the plus or minus there. Now what we want to do to find the possibilities is we're going to divide all the p-values by all the q-values. Okay, so when I do that now, I'm going to start with the 1. I'm going to divide 1 by 1, which is going to give us 1. Now, again, we have a plus or minus 1 and over a plus or minus 1. So any combination of those things is going to give us a positive 1 or a negative 1. So this is actually going to be plus or minus 1. All right, then we're going to go to the 2. So again, I'm going to divide. 2 divided by 1 is going to give us 2. But again, because it's a positive or a negative 2 divided by a positive or a negative 1, we're going to end up with a plus or minus 2 as our possibilities there. That means we actually have 4 potential options for our zeros. We have a positive 1, a negative 1, a positive 2, and a negative 2, right? So those are all the possibilities. 1, negative 1, 2, and negative 2. Now what we're going to do is we're going to take each one of those and we're going to test them to see if they're actual zeros. And the way we're going to test is we're going to use synthetic division. So I'm going to start with my 1. I'm going to put it in my box. Now I'm going to list out all the coefficients of my polynomial. That's 1. Notice here we don't have an x squared term, so I need to use a 0 for the x squared. And we have a negative 3 for the x term and a 2 for the constant. As always, we bring down that first term, so bring down the 1. Now we multiply. 1 times 1 is 1. Now we're adding. 0 plus 1 is 1. 1 times 1 is 1. Negative 3 plus 1 is a negative 2. Negative 2 times 1 is negative 2. And 2 plus negative 2 gives us 0. In this case, because we get 0 as the remainder, that tells us that this is one of our zeros now, right? So in terms of listing out our zeros, we know that positive 1 is one of those zeros. All right. Now we're going to go to the next one, -1. So again, I'm going to put -1 in my box. Same coefficients I had before, 1, 0, -3, and 2. Bring down the 1. 1 times -1 is -1. 0 plus -1 is going to give us -1. -1 times -1 is +1. -3 plus 1 is going to be -2. -2 times -1 is +2. And then 2 plus 2 is 4. In this case, we do not get a remainder of 0. That means that this is not a 0 of our polynomial, so this one does not work. So far, the only one that we've got is 1. Still got 2 more to test, though. So now we're going to test the +2. And 2, same coefficients, 1, 0, -3, and 2. Bring down the 1. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. -3 plus 4 is 1. 1 times 2 is 2. And 2 plus 2 is 4. I did not get a remainder of 0. Therefore, this is not one of my zeros. And then the last one we have to check is -2. -2 in our box. Same coefficients. Bring down the 1. 1 times -2 is -2. 0 plus -2 is -2. -2 times -2 is 4. -3 plus 4 is 1. 1 times -2 is -2. And 2 plus -2 is 0. This time I do get a remainder of 0. That means that this is a 0 of my polynomial. And so therefore, -2 is the other 0. All right, so that's all we're doing in this section is figuring out what are the possibilities of rational zeros using our p's over q's. Once we know the possibilities, then we can test them using synthetic division, and then we're going to see which ones actually give us a remainder of 0. All right, so now we're going to write this polynomial in factored form, and the way we're going to do that is we're going to find all the zeros, which should give us all the factors. Okay, so first thing again, we want to do our p's and q's. I'm going to think about my p values here. Remember, the p's are going to be the factors of the constant term. Well, in this case, my constant term is the 6. So I'm thinking about the factors of 6. Well, factors of 6, and remember, it's always going to be plus or minus. You have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Because 1 times 6 would give us 6, 2 times 3 would also give us 6. In this case, we could have some combination of negatives and positives that would still give us a positive 6. Now we look at the q values. Again, the q values are going to come from the leading coefficient. So this time we're looking at the 2. Factors of 2 are just 1 and 2. So we're going to have plus or minus 1 and plus or minus 2. Now we have to do our p over q's. So when I do that, I'm just going to go straight down my list. I'm going to divide every p by just the first q value first. So that's taking each one of my p values and dividing it by 1. Well, 1 divided by 1 is 1, so we get plus or minus 1. 2 divided by 1 is 2, so plus or minus 2. 3 divided by 1 is 3, so plus or minus 3. And 6 divided by 1 is 6, plus or minus 6. Now I need to go down the list and divide every single p value by the 2. So we have 1 divided by 2, that's 1/2, so plus or minus 1/2. 2 divided by 2 is 1. I've already got 1 on my list. I don't need to list it again, so I'm not going to repeat it. 3 divided by 2 is 3/2, so plus or minus 3 over 2. And then plus or minus 6 over plus or minus 2 is going to be 3. And we already have plus or minus 3 on our list, so we don't need to list it again. So don't worry about repetitions, right? We don't need to list them twice because we're already going to test them anyway. All right, so this is my list now of all the possibilities of rational zeros for this polynomial. Keep in mind, not all of these are going to work, right? We have to test and see which ones will. Now, what I'm going to tell you is you will have access to Desmos or a graphing calculator on your test. I would not go through and do synthetic division on every single one of these, because notice here, there's 1, 2, 3, 4, 5, 6 times 2, because they're all plus or minus. So there's 12 options to test here, right? I don't want you testing all 12 of these. So what I'm going to do now is I'm actually going to graph this polynomial, see where the zeros might be just based off the graph, and that'll give me an idea of which ones of these I might actually want to test. Okay, so I'm going to switch over to Desmos. All right, and so I'm going to put in this polynomial. So we've got x equals 2x cubed plus x squared minus 13x plus 6. So now looking at my graph, right, and I'm not actually going to click on the zeros because I don't want to know for sure. I just want to get an idea of where they might be. I've got one between -4 and -2, right? So -3 looks like it might be a possibility, right? So I'm going to say -3 is probably one that I want to test here. I also have one that looks like it's probably at +2. So +2 is probably another one I want to test. And then I've got the one that's just to the right of 0, and it looks like it's before I get to +1. So that could be, the +1/2. So +1/2 is probably another one to test, right? And again, if you're on your graphing calculator, it's going to be even more difficult to determine exactly where these values are. So again, this is just kind of give us an idea of which ones do we even want to bother testing, so that we don't have to test all 12 of them. All right, so I'm going to start with those three, the -3, the +2, and the +1/2. We'll use synthetic division, and we'll see if those work. And if they don't, then we'll test different ones, right? All right, so here are the possibles, right? The -3, the 2, and the 1/2 that I just mentioned. Start with the -3. I'm going to go -3 in my box here. Coefficients this time, we have a 2. Coefficient of x squared is 1. Coefficient of x is -13. And then we have our constant term of 6. No missing terms this time, so no zeros. Bring down the 2. Now we multiply. 2 times -3 is -6. Now we're adding. 1 plus -6 is -5. -5 times -3 is 15. -13 plus 15 gives us 2. 2 times -3 is -6. And when I add those together, I do indeed get a remainder of 0. So this one checks out. Okay, so now in terms of listing out my zeros, I know that -3 is one of those zeros. Now, what I want to explain to you is we don't necessarily need to continue doing synthetic division at this point. Because if you remember, once we've done the synthetic division once, we know that what's left on that line represents something that has a degree 1 less than whatever we started with. So in this case, we started with x cubed. That means that our line in our synthetic division there gives us an x squared term. So this right here is actually 2x squared minus 5x plus 2. That would be the factor that's left over. And then the factor that we have from the -3 is going to be x plus 3. So that's what I know now about my factored form. So then I would look and see, well, is there anything else I could do to factor 2x squared minus 5x plus 2? So let's see if that factors, and then I don't have to do synthetic division anymore. Okay, so the factors of 2x here are just going to be 2x and x. Factors of 2 are going to be 1 and 2. Now keep in mind we need to get a -5x in the middle. I'm going to put my 2 down here and my 1 here so that I end up with a 4x on the outside and a 1x on the inside. In this case, both of those are going to need to be negative to give me the +2 and to also give me the -5x in the middle. So we're going to have a minus and a minus. Now, what that means is those are the factors of the 2x squared minus 5x plus 2. Therefore, I can set each one of those equal to 0 to get my other 2 zeros now. And if I do that, when I add 1 here and divide by 2, that's going to give us x equals 1/2. And then over here, we're going to get x equals 2. So indeed, 2 and 1/2 are the other two zeros that actually work here. Now, the reason I did it that way rather than just continuing on with my synthetic division is I wanted the factored form anyway. So in this case, now I have my completely factored form. That's what I'm boxing in right here. And I have my list of all of my zeros right here. So those are the two things we were asked for in this case, were the factored form and the zeros, and that's what we have now. So once you've done your synthetic division, you get it down to something that's an x squared, then you can see if that factors, right? And if it doesn't, you can actually use quadratic formula, and we'll look at that down the road. Okay, so it is a possibility that you get something that doesn't factor, but then we can at least use quadratic formula to find those other zeros at that point. All right, so now we've got an x to the fourth polynomial, x to the fourth minus 5x cubed minus 5x squared plus 23x plus 10. Again, we want to find all the zeros, and it says we're going to sketch the graph. We're actually going to use the graph in Desmos to help us figure out which zeros to test anyway. But this time we don't need the factored form, just all the zeros. And so again, my first step here is I'm going to list out all my p's and q's. Let's start with our p-values. Again, that comes from our constant term down here at the end. So we're thinking about the factors of 10. Remember, everything's going to be plus or minus. So plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Because 1 times 10 is 10, 2 times 5 is 10. Those are the only factors, and we just have to put plus or minus on all of them. Now let's think about the q's. Again, that comes from our leading coefficient. In this case, that's the understood 1. So my only factors for q this time are plus or minus 1. Now we're going to do p over q. Again, we're just going to go down the list, take all of our p values, divide them by all of our q values. Well, in this case, we're just dividing all the p's by 1. So that's just going to give us plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So again, that's 8 options that we would need to test, right? Because we have 4 numbers, all with a plus or minus, so that doubles that value, right? So that's going to give us 8 total. So rather than testing all 8 of those, I'm going to go to my graph now. I'm going to see which ones look like they might work, and those are the ones I'm going to check with synthetic division now. Right. So now in Desmos, I'm going to graph my polynomial, and f of x equals x to the fourth minus 5x cubed minus 5x squared, 23x plus 10. All right, so again, just looking at the graph now, in terms of possibilities, it looks like -2 is one place that it might cross. Okay, so I'm going to list that one. Then we've got one over between 4 and 6, right? That looks like 5. That's a possibility. Then we've got these other ones, right? One that's slightly to the left of 0, so something in the negatives, not to -1 though. That's a decimal value. It's not even on my list, right? So I don't know what that value is going to be, but it's not one of my possibilities for my rational zeros, so I'm not going to test that. Same thing with the one to the right of 2, right? I don't have any decimal values now that are somewhere between 2 and 3 on my list of possible zeros, rational zeros, so I'm not going to test that. So -2 and 5 are the only two that I feel really sure about right now that I'm going to use my synthetic division with. Okay. All right, so we're going to go with -2 first. -2. Again, list out all of your coefficients. I don't have any missing terms, so it's just going to be 1, -5, -5, 23, and 10. Bring down your 1. 1 times -2 is -2. Now we add -5 plus -2 is -7. -7 times -2 is 14. Negative 5 plus 14 is 9. 9 times negative 2 is negative 18. 23 plus a negative 18 is 5. 5 times negative 2 is negative 10. And 10 plus negative 10 is 0. So that does check out. Okay, so that tells us now that in terms of actual zeros, negative 2 is one of those zeros. Now, that's only going to get us down to an x cubed, right? Because we started with x to the fourth, we divided out one of our x's. Okay, so now we're left with an x cubed polynomial on this line right here. That's not enough to factor yet. So what I'm going to do now is I'm going to go with my 5, but rather than going back to the original list of coefficients, I'm going to continue from right here. Because if 5 is a 0 of the original polynomial, it should also be a 0 of whatever polynomial we're left with here. Okay, I'm just going to work with these coefficients now rather than going back to the original. When I do that now, I'm going to bring down my 1. 1 times 5 is 5. Negative 7 plus 5 is negative 2. Negative 2 times 5 is negative 10. 9 plus negative 10 is negative 1. And negative 1 times 5 is negative 5 for a remainder of 0. So again, that checks out. And so now I know that 5 is also a 0 of that polynomial. So now let's think about in terms of factors what we have. Well, the negative 2 means that we have a factor of x plus 2. The 5 means we have a factor of x minus 5. And now this line that's left down here is an x squared factor because we started with x to the fourth and we've divided out two x's, right? So now this line is actually x squared minus 2x minus 1. Now, at that point, we could try factoring the x squared minus 2x minus 1. Now, here's what I'm going to tell you. The only factors of 1 are 1 and 1. But because it's a negative 1, we know 1 would need to be positive, 1 would need to be negative. That's not going to give us a negative 2x. Okay, so this thing down here actually does not factor any further. So we've got our zeros now of negative 2 and 5. But remember back to the graph, there were two other places where we crossed the x-axis, meaning we have two other zeros. We want to find all the zeros here. So what we're going to have to do is think about how we're going to find the zeros of x squared minus 2x minus 1. And since it doesn't factor, our option is quadratic formula now. Okay, so I'm going to do quadratic formula to find my last two zeros, those places where it crossed the x-axis that were decimals, right, that we couldn't actually find using our rational zeros. So when I do that now, I'm going to have x equals, remember our quadratic formula starts with negative b, so that's going to become a positive 2, plus or minus the square root of b squared, so negative 2 squared, minus 4ac, 4 times 1 times negative 1, all over 2a, 2 times 1. Right, now we simplify that. So we've got 2 plus or minus the square root. Negative 2 squared is 4. Negative 4 times 1 times negative 1 is going to give us a positive 4, all over 2 times 1, which is just 2. Right, 4 plus 4 is 8. So now we're left with x equals 2 plus or minus the square root of 8 over 2. And now we just need to simplify that square root of 8. Okay, so when we do that, remember the factors will be 4 and 2, and we can bring out the square root of 4. So we're basically breaking this down into the square root of 4 times 2. Square root of 4 is 2. Keep the other 2 inside. So this is 2 plus or minus 2 square root of 2 all over 2. But now because we have a common factor of 2 in each of those terms in the numerator, we can actually divide. 2 divided by 2 is 1, plus or minus 2 square root of 2 divided by 2. The 2's are going to cancel and leave us with square root of 2. And so now our other zeros are 1 plus the square root of 2 and 1 minus the square root of 2. And that's why it looked like on our graph that we had decimal values. Okay, and so if you were to actually go back and click on those points in Desmos and get the decimal values, those decimals should match the decimal values for 1 plus square root of 2 and 1 minus square root of 2. That's why they did not show up in our list of rational zeros, because those are irrational values. They're not going to show up in that list of rationals. But again, in this case, we were just looking for all the zeros. Here is our list of zeros for that polynomial now. So again, just to kind of recap, always start with P's and Q's, factors of your constant, factors of your leading coefficient. Do your division to get your list of P's over Q's. That's your possible rational zeros. Then I would take a look at the graph to see which ones of those might actually work, right? That way you're not testing all 8 of these. Once we verify that we have, 1, 2, 3, 4, however many that actually do work, see what's left over, because if you can factor it, you could factor it to find the other ones. Or if it doesn't factor and it's quadratic, then you can use quadratic formula to get those irrational ones, right, that showed up on our graph but don't show up on our list of rational zeros. All right, now Descartes' rule of signs. So we're going to let P be the polynomial that we've been looking at with real coefficients. The number of positive real zeros of P of X either is equal to the number of variations in sign in P of X, or is less than that by an even whole number. So basically what we're going to be doing now is we're going to be going down our P of X and figuring out how many times does the sign change from term to term. That's going to give us the number of positive real zeros, or the number of positive real zeros is going to be less than that by an even whole number, meaning that if I get 5 variations in sign, then I can subtract 2 from that and say, well, there could be 3. I can subtract 2 from that and say, well, there could be 1. Okay, but you're basically just subtracting 2 from whatever number you get in variation in sign, and that would give you the options, the possibilities for the number of positive real zeros. Now, the number of negative real zeros is either equal to the number of variations in sign in P of negative X, or again, is less than that by an even whole number. So to figure this out, we're going to substitute negative X in, we're going to simplify it, and then we're going to determine how many variations in sign we have. Then our number is going to be of negative real zeros is going to be equal to the number of sign changes, or again is going to be less than that by an even number, so we can just subtract 2 over and over again to figure out the options. All right, so I'm going to use Descartes' rule of signs here to determine the possible number of positive and negative real zeros of this polynomial. So the first thing I'm looking for is how many times does my sign change just in P of X in general. So I'm looking here, my first term is positive. So we have to start with whatever coefficient we have. In this case, we start with a positive. Our next term, also positive. The next term is also positive. Now the next term becomes negative, and the last term is also negative. So if I'm going down, I'm only looking for where do the signs change? How many sign changes do I have? I went from positive to positive, that's not a change. Then I went from positive to positive, not a change. Then I went from positive to negative. Here is our first sign change in that polynomial. And then it went from negative to negative. The sign did not change there. So in this case, there's only one sign change. So in terms of positive real zeros, there can only be one. So that's what Descartes' rule of sign tells us now, is that if we go down our list, right down the polynomial, and say how many times does our sign change, that tells us how many positive real zeros we could have. But again, let's say we had gotten 5 sign changes, then it could be 5 or 3 or 1, right? We're not guaranteed 5 positive real zeros in that case. All right, now for negative real zeros, we want to look at P of negative X. So now I actually need to substitute a negative x into my polynomial. So we're going to have 3 times negative x to the 6th plus 4 times negative x to the 5th plus 3 times negative x to the 3rd minus negative x minus 3. All right, now if we simplify this, remember a negative to an even power is going to become positive. So this first term becomes 3x to the 6th. Negative x to the 5th power, that's an odd power. This is going to be a minus 4x to the 5th. Negative x to the 3rd power, again, odd power is going to be negative, so negative 3x cubed. A minus a negative x now is going to become a positive, so plus x. And then we still have our minus 3 down at the end. Again, I'm looking for the number of sign changes now. So I'm just going to go down my list, figure out how many positives and negatives I have, and then we'll count up how many times the sign changes. My first term here is a positive. My next term is a negative. Negative 3x cubed is a negative. Positive x is positive, and then negative 3 is negative. So now we start with a positive. We're only looking for sign changes. Well, from positive to negative here, that's one sign change. Then it goes from negative to negative. That's not a change. Then it goes back from negative to positive. That's a second sign change. And then finally, we go from a positive to a negative. That's a third sign change. So in terms of negative real zeros, I could have 3 negative real zeros. But remember, we said it could be less than that by an even whole number, meaning that I need to subtract 2 from that and say, well, I could also just have 1 negative real zero. So it's possible I have 3. It's also possible I have 1. And we just want to keep subtracting 2 until we get to a point where we can't anymore, right? Because if I subtract 2 again, I'm in the negatives. We can't have a negative number of zeros, okay? So in this case, it's either 3 or 1, and only 1 positive real zero. The reason this is useful is that when we're doing our test, let's say we don't have a graphing calculator or Desmos available to us. Then when we're doing our synthetic division to test these rational zeros, once I find one positive one that works, there's no reason to test any more positives because I know that's as many as I can have. Same thing with the negatives, right? If I find 3 negatives that work, then I know that's all the negative ones. There's no reason to test any more negatives. Then I can just test positives from there on out, okay? So that's why Descartes' rule of signs is important. It helps us to narrow down which values we actually want to test so that we don't have to test these really long lists of values. All right, now upper and lower bounds. Okay, so again, we're going to let P be a polynomial with real coefficients. If we divide P of x by a factor x minus b, where b is bigger than 0, using synthetic division, and if the row that contains the quotient and remainder has no negative entries, then we call b an upper bound for the real zeros of P. What that means is, let's say we put in a b value into our box, and it turns out not to actually be a 0. It doesn't actually work. But everything on that line at the bottom comes out positive. There's no negative values there. Then we can say that b is an upper bound for all the real zeros of P, meaning there's no zeros that are going to be bigger than that value. Again, this is useful because then we know, well, there's no reason to test any of our list that's bigger than that value that we just put in. Even though that one didn't work, if everything comes out non-negative, okay, and we have to say non-negative because we could have zeros in there also. And in this case, as long as there's no negative values on that list, on that line, then we know that it's an upper bound and all of our other zeros have to be less than that value. Now, number 2 says, if we divide by some other factor, right, using synthetic division, and what we get in the quotient row alternates non-positive and non-negative. And again, we can't just say positive and negative because zeros could be in there also. Okay, but if it alternates non-positive, non-negative, then A is a lower bound, and then we know there's no reason to test anything smaller than that value. Okay, So again, this narrows down our list so that we don't have to test every single value on that list if we can find these upper and lower bounds now. All right, so now what we want to do is show that all the zeros of this polynomial are somewhere between -3 and +2. In other words, we want to show that this value here is a lower bound because there can't be anything smaller than that. And we want to show that this value is an upper bound because there can't be anything larger than that one. So we're going to use that upper and lower bound rule that we just looked at to show here that -3 is a lower bound, +2 is an upper bound. And if we can show that, then we know that all of our zeros have to be between those two values. So I'm going to start here with -3. I'm going to list out my coefficients. So we start with 1. This time we're missing the x cubed term, so I'm going to put a 0. Then we have -3, +2, and -5. Bring down your 1. 1 times -3 is -3. 0 plus -3 is -3. -3 times -3 is 9. -3 plus 9 is 6. 6 times -3 is -18. 2 plus -18 is -16. -16 times -3 is 48. And -5 plus 48 is 43. Okay. So if we look at that row now, where the quotient and remainder are, notice we start with a positive, then it goes to a negative, then it goes to a positive, then negative, then positive. So this row alternates positive, negative, positive, negative, positive, negative. Or in other words, right, we have to think of this as non-positive, non-negative. So we have a non-negative value here, a non-positive value here, non-negative, non-positive, and non-negative. And again, the reason we have to think of it that way is because there could be zeros in there, right? And we're going to look at an example of what happens in that case. Now, because that happens, we can say that this is indeed a lower bound of the zeros of that polynomial. Since it alternates non-negative, non-positive all the way down, now we know we have a lower bound. Now we need to show that 2 is an upper bound. Test 2, same coefficients, 1, 0, -3, 2, and -5. Bring down the 1. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. -3 plus 4 is 1. 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. And -5 plus 8 is 3. Now we look down our list. Remember, we need all non-negative values now. Okay, so 1 in this case is not negative. 2 also non-negative. 1 is non-negative. 4 is non-negative. And 3 is also non-negative. I know you might be saying, why can't we just call them positives? Again, because if there's zeros in there, we have to be careful of how we label them. Okay, and so I'm labeling all of these as non-negative values. Now, because we get an entire list of non-negative values, that does tell us here that this is an upper bound. And now we've proven that all of our zeros of that polynomial have to be somewhere between -3 and +2. And again, that's useful because if you were going through and finding your possibilities here, right, the factors of 5 are going to give you plus or minus 5 for sure. Well, I know that +5 and -5 can't work now because those are outside of that upper and lower bound, right? So there would be no reason to even test those values using synthetic division. I would only want to test the values that are between -3 and +2. All right, so now, same thing, we're trying to show upper and lower bounds, okay? So we want to show that all the real zeros of this polynomial are greater than or equal to -4. So, in other words, we want to show that this value here is a lower bound. We want all of our zeros to be bigger than that value. So, I'm going to put -4 in my box. I'm going to list out all of my coefficients. This time there are no missing terms. We have 1, 4, 3, 7, -5. Now we bring down the 1. 1 times negative 4 is negative 4. 4 plus negative 4 is 0. 0 times negative 4 is 0. 3 plus 0 is 3. 3 times negative 4 is negative 12. 7 plus negative 12 is negative 5. Negative 5 times negative 4 is 20. Negative 5 plus 20 is 15. All right, so now if we're trying to show that this is a lower bound of our polynomial, we need alternating non-negative, non-positive. So I'm going to start with that first term. In this case, 1 is a non-negative value because 1 is not negative. Now, the next thing we get here is a 0. 0 can be considered either non-negative or non-positive, right? Because it's both, right? 0 is not negative and it's also not positive. Well, because I'm trying to show this is a lower bound, I need this to alternate non-negative, non-positive. So I'm going to call 0 a non-positive for this particular question. You can label it whichever you want, right? So however you're trying to use it, it could be either one. Now 3 is a non-negative. Negative 5 is non-positive. And 15 is non-negative. So now we have alternating non-negative, non-positive. That tells us that this is a lower bound, and therefore all of our zeros have to be bigger than negative 4. So again, that's how you're going to treat 0, right? It can be either non-negative or non-positive. You can call it either one you want, but in this case, because we need this to alternate non-negative, non-positive, we're going to call that 0 a non-positive value. All right, example 7. So now we want to factor completely this polynomial. We have 2x to the 5th plus 5x to the 4th minus 8x cubed minus 14x squared plus 6x plus 9. All right, so our first step here is we want to figure out the p and q values. So I'm going to start with p's. Remember, that's our factors of our constant. So we're thinking about the factors of 9 here. So plus or minus 1, plus or minus 3, and plus or minus 9. Now I'm going to list out my q values, which are just the factors of the leading coefficient, which is 2. So plus or minus 1 and plus or minus 2. Now we divide. So p over q. Again, I'm going to take all my p values over each q value now. So 1 over 1 is going to give us plus or minus 1. 3 over 1 is plus or minus 3. 9 over 1 is plus or minus 9. Now divide each one by 2. 1 over 2 is plus or minus 1/2. 3 over 2 is plus or minus 3/2. And then 9 over 2 is plus or minus 9/2. So again, that's a long list of values now, right? So we actually have 12 different values that we would need to test. But we're not going to test them all, right? I'm going to go to my graph next. I'm going to see which ones look like they might work, and those are the ones I'm going to start with. So let's graph this in Desmos now. Two x to the 5th plus 5x to the 4th minus 8x cubed minus 14x squared plus 6x plus 9. All right, so now looking at that graph, it looks like we've got one that's slightly to the right of 2. And I'm not really seeing anything else where this one crosses the x-axis, right? So in terms of our options, Make sure I have that graphed correctly. Sorry. Oh, I left out my x. That's why. There we go. That's better. Okay, so that's what our graph should look like now. Okay, so if we look at our graph, it looks like we've got one somewhere between -2 and -4. So that could probably be a -3. That was one of our options. So -3 is probably one we want to test. Now we have one between 0 and -2. So that looks like -1. -1 was on our list, so we could check that one. We also have one now somewhere between 0 and 2. That looks like it could be +1. And then there's one slightly to the right of that, which could be 1.5. And 3/2 was one of our possibilities. Now, the other thing I do want to point out in this case is notice that the one at -1 looks like it bounces there. And so remember, that means that it might have an even multiplicity, okay, meaning that it could happen twice. So when we get down to the factors, right, we'll see if that actually does happen. But just keep in mind that that -1, because it bounces there, could have an even multiplicity. All right, so now let's go back. Let's actually test these and see which ones actually work now. All right, so we said -3 looked like it could work. I'll put -3 in my box. Coefficients here, we're not missing any terms. So we've got 2, 5, -8, -14, 6, and 9. Bring down the 2. 2 times -3 is -6. 5 plus -6 is -1. -1 times -3 is 3. -8 plus 3 is -5. -5 times -3 is 15. -14 plus 15 is 1. 1 times -3 is -3. 6 plus -3 is 3. 3 times -3, -9. And that gives us a remainder of 0. And so -3 is one of our zeros now. Now, again, we can continue on from that line, right? We don't need to go back to the original coefficients. So -1 is the next one on my list. I'm going to test -1. I'm going to continue right on from those. So bring down the 2. 2 times -1 is -2. -1 plus -2 is -3. -3 times -1 is 3. -5 plus 3, -2. -2 times -1 is 2. 1 plus 2 is 3, and 3 times -1 is -3 for a remainder of 0. That checks out. So -1 is also one of my zeros. Now remember, this time we started with x to the 5th power. We've divided out 2 x's so far, so we're only down to x to the 3rd. We still don't have enough that we can actually factor what's left. So we need at least one more to get us there. So let's go with the 1, see if 1 works. Bring down the 2. 2 times 1 is 2. -3 plus 2 is -1. -1 times 1 is -1. -2 plus -1 is -3. -3 times 1 is -3. That gives us a remainder of 0. That checks out. So 1 is also a 0 now. All right, so now what I'm left with is going to be quadratic, right? We're going to have an x squared term here because I've divided out 3 of my x's from x to the 5th. So now I'm left with x squared. So I know my factors so far are x plus 3 from the -3, x plus 1 from the -1, x minus 1 from the +1, and now this line tells us 2x squared minus 1x minus 3. So now I'm going to see if I can factor that quadratic. So just bring down everything else. In this case, to get a 2x squared, we need a 2x and an x. To get a 3, we need a 3 and a 1. In this case, I want a -x in the middle, so I'm going to put my 3 here and my 1 here. I know my signs need to be opposites, one positive, one negative. I need the 3 to be the negative, since it's larger, to give us the -x in the middle. And so that right there is the factored form. That's what we were looking for this entire polynomial now. Now, if you look, we actually have this x plus 1 that's repeated. And so if you wanted to combine those and write it as x plus 1 squared, you could. We'd have x plus 3 times x plus 1 squared times x minus 1 times 2x minus 3, right? So either one of those is acceptable. The second one is a little more simplified, right, because we've combined the x plus 1. But notice that that negative 1 then is what we call a double root. And that's what we said on the graph, right? It looked like negative 1 bounced there. Okay, and so that has an even multiplicity. In this case, it does happen twice. And then our last 0 in this case is the 3/2, but you can see that from that last factor. So the key on these problems now is, I need to see the P's and Q's. I need to see that you've tested the ones that you think work, right? But use your graph to help you figure out which ones might work so that you're not testing all 12 in this case. And also pay attention to the directions, right? Sometimes you're going to be asked to find zeros. Sometimes you're going to be asked to factor completely. Sometimes you want both, right? And usually on the test, that's what I'm going to ask for, is to list out all the zeros and to list out all the factors. All right, so that's all we've got for section 3.4. As always, send me those questions in WebAssign as you have them. Come see me during student hours if you need to. Have a great day, and I will see you next time.